Hey guys, Dr. Cadell, and this is the Freezing Point Depression Lab. The idea behind the experiment today is that whenever you have a pure substance, it melts, freezes, same thing, at a certain temperature, and it boils at a certain temperature. Whenever you dissolve something in that substance, you have a solution. Now that solution consists of the solute, the thing that's dissolved in it, and the solvent, the thing that it's being dissolved in. So if you put some salt and put it into water, water would be the solvent, salt would be the solute. Now whenever you add a solute to a solvent, the freezing point, the melting point of that solvent goes down. It lowers every single time. And by the way, also the boiling point raises. This is the reason why they put salt on the roads up in the mountains where it snows, because when you put salt on the roads, basically you made a solution whenever it snows, and now the freezing point of that solution is lower than the freezing point, than the temperature all around it. Everything around it is going to be about 32 degrees Fahrenheit, and it's not going to melt there. It's going to stay liquid and not iced over. So what we're going to do is we're going to use the freezing point depression equation. That's this guy right here. And what it says is this: the delta TF, that means the change in the freezing point, I'll explain that in just a second, is equal to negative MKF. I'm going to tell you what each of these terms means. So the delta TF is this. It's the change in the freezing point when you add that solute to the solvent. So water freezes at 0 Celsius when it's just water. If you add some salt, it freezes at some lower temperature, -1, -2, something like that, depends on how much salt you put in it. And now the delta TF would be the freezing point with the solute in it, with the salt in it, minus the freezing point without the solute, just a pure solvent. So that's what delta TF is. M is a unit of concentration called molality. Not molarity, but molality. And this is an important definition. This is the definition of molality. Moles of the solute, the thing you're dissolving in there, divided by kilograms of the solvent, the thing you're dissolving it in. And so what we're going to do, and the K sub F. This is just a constant, and it depends upon what the solvent is. So I give you the value for K sub F in the lab, so you'll know what that is. So we know this. What we're going to do in the experiment is we're going to measure our delta TF. I'll tell you how we do that in just a minute. But what that means is then we can solve this equation for the molality. It's going to be some number, because we're going to measure the two temperatures. We're going to know this. We're going to find what the molality of that solution is. And that's going to be, the molality is going to be the moles of your unknown divided by the kilograms of lauric acid, which is what you're dissolving your unknown in. Once we know the molality, it's real easy to find the moles of the solute, the moles of your unknown, because the solvent, the lauric acid, we're going to weigh that. And so we'll know how many grams, and that means how many kilograms of our solvent we have. So if we just take this number here, multiply it by the kilograms of lauric acid that we weigh out, this cancels, and what we have left is the moles of solute. And so that's really nice, because if we can find the moles of the solute, guys, our goal in this whole experiment is to find the molar mass of our unknown, our solute. And the molar mass, remember, this is grams over moles. Well, this is how we get the moles. We take, the molality that we get from this equation, multiply it by the kilograms of the solvent, the lauric acid, and that gives us our moles, which goes down here. The grams, that's easy. We're going to weigh their solute, and once we know that, we have everything we need. So remember, this is sometimes people forget this or get confused. The solute is the unknown. The solvent is the lauric acid. And so let's go over and get started doing the experiment. All right, guys. So we're basically going to follow the same process 4 times. What we're going to do is we're going to determine the freezing point of the pure solvent, which is lauric acid, 2 times, and then we're going to add some of your unknown, which is the solute, and do the same thing 2 more times. So for the lauric acid, we're going to weigh out some lauric acid first. Now, what we're going to do is going to use a large test tube. We don't care how much the test tube weighs. We're going to put it in a beaker. We don't care how much the beaker weighs. So what we do is we put the beaker with the empty test tube on the balance, just like before. Close the door, we tear the balance. So now balance should say 0. with the beaker and the test tube on it. Once we do that, we take it out, so it's zeroed out, tear it out, and we're gonna fill this guy up pretty much all the way. We're going to see how much it weighs. However much it weighs when we get it filled up, with just a little space at the top to put the rubber stopper in, that's how much it's going to be. The reason we want to make sure that it's as full as we can get it is that when this stuff melts, it actually shrinks, it condenses, and the level goes down, and we need to make sure that we have our thermometer all the way down inside of it because we're going to measure its temperature. So now what I'm going to do is I'm going to take my rubber stopper that I have. It's a one-hole rubber stopper. And we always do this with rubber stoppers before we put them in glassware. There's a wide end and a narrow end. We take the wide end and make sure it does not fit in the hole, because if it does, when we turn it around this way and put it the way it's supposed to go, it'll go all the way in and then get stuck. And you have to break the glass to get it out. But I have that about as full as I can get it with the test tube in there, the stopper in there. Now I'm not going to weigh the stopper because we just care about how much this weighs. Put it back in, close the balance, read that number from the balance. That's the mass of your solute, mass of lauric acid, which is A1. That number is A1. I'm going to take it out, put the rubber stopper in, and I'm going to put it in this boiling water, holding it with this ring stand, test tube clamp. Now, this is hot, so if I have to move it, I'm not going to touch it with my hands. I use some beaker tongs, and that's what it's for. Just move it around. Submerge it as much as I can. It doesn't matter, guys, that it's not all the way submerged. There's a little bit of lauric acid on top, because you'll see as it melts, it's gonna shrink down. Okay, so once that has finished melting, we're going to take it out. And we're going to put the thermometer in there, and we're going to agitate it, and we're just going to record the temperature in this table every 10 seconds until it solidifies, and then the temperature stays the same and starts decreasing again. Once the temperature has gone down, stays the same, and starts decreasing. Once we hit the decreasing part, we can stop. What happens is whenever anything is melting or freezing, or, by the way, boiling or condensing, the temperature always stays the same during that entire phase change. That's a good thing to know. So you can see it's almost melted right there. We'll be able to tell. It's real easy because we can see the white lauric acid. When it's all melted, it'll be clear. It looks like water. It's a clear liquid. All right, guys, so now that the lauric acid has all dissolved, we're going to start recording our temperatures every 10 seconds as it freezes. Now, to take it out, this is really hot over here, so we're just going to lift it up over here. This is not hot. I'm going to take my thermometer, use the digital thermometer, place it in here, and just keep on shaking it and recording the temperature every 10 seconds. All right, guys, so now that the lauric acid has completely frozen, temperature stayed the same for a while and then started dropping down, we can stop. So we recorded our temperatures in our data table, but the only number that we need is the temperature that it stayed at the longest. That's what we're going to call our freezing point. That's the number we need. That will be the freezing point of just the solid. So what we're going to do now is we need to melt this again. Get that out. So we're going to put it over here, and as we're waiting for it to melt again, we are going to weigh out our unknown. Our unknown is the solute. That's what it looks like. And so we're going to take a weigh boat right here and put it on the balance, tear it out, because we don't care what the weigh boat weighs. It says 0 with the weigh boat on it. Take it out. Take all of our unknown, dump it into the weigh boat. Take our unknown number off of our test tube that our unknown came in, and just tape it in our data table. If you have an unknown number, it will be a 2 for you. Put this guy back on the balance, close the doors. That number is the mass of the solute, which is the mass of the unknown. That's going to be A3. Take it out. Using a funnel, we're going to add it to our test tube with our lauric acid in it. It doesn't matter that it's not melted all yet. It's all in there. And now what we do is we're going to wait for this to melt entirely. And once it does, we're just going to follow the same process we did with the pure lauric acid. Going to take it out, agitate it, record the temperature every 10 seconds until it solidifies. Temperature stays the same for a while and starts decreasing. The temperature that it stays at the longest will be the freezing point of the solution. And that's going to be the experiment. There we go.